Hi everyone, welcome to Education Hub Zone. So today we are going to discuss about physical chemistry. The topic is solution. Before getting started, please don't forget to like, share and subscribe on our YouTube channel for more upcoming videos. Okay, let's get started. Solution. A solution is a homogeneous mixture of two or more substances. A solution which contains two substances is called binary solution. The substance which is dissolved is called solute, and the substance which dissolves the solute is termed as solvent. Solids and gases dissolve in a liquid to a limited extent. The extent of dissolving a solute in liquid or solvent is expressed in terms of solubility. Miscibility is the solubility of liquid in another liquid, where there is completely miscible, example water and alcohol, and immiscible, example kerosene and water. Composition of solutions. Molarity is the number of moles of solute dissolved in 1 liter of the solution. Molarity equals to number of moles divided by volume. Units of molarity are mole per m cubic or mole per liter or molar. But number of moles equals to mass over molar mass. Then molarity equals to mass divided by molar mass times volume. Molality is the number of moles of solute per kilogram of solvent. Molality equals to number of moles of solute divided by mass of solvent in kilogram. Molality equals to mass of solute divided by molar mass of solute times mass of solvent in kilogram. If the mass of solvent is given in grams, then molality equals to mass of solute times 1000 divided by molar mass of solute times mass of solvent. Normality is the number of moles equivalent per liter of solution. Normality equals to Z times molarity, where Z equals to valency. Since we are dealing with acids and bases, then Z equals to basicity or acidity. Recall, basicity is the number of hydrogen atoms replaceable by a base in a particular acid. For example, hydrochloric basicity equals to 1, sulfuric basicity equals to 2. Acidity is the number of hydroxyl ion that can be donated. For example, sodium hydroxide acidity equals to 1, aluminium hydroxide acidity equals to 3. Mole fraction. For two liquids A and B, mole fraction of A equals to number of moles of A divided by number of moles of A plus number of moles of B. Also, mole fraction of A plus mole fraction of B equals to 1. Colligative properties. Colligative properties of a solution are properties of a solution that only depends on the number of solute particles added and not on the type of solute dissolved. There are 4 colligative properties: lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. Assumptions of colligative properties. The solute should not react with solvent. The solute should not be volatile compared to solvent. The solute should not dissociate or associate in the solvent. A. Lowering of vapor pressure. Vapor pressure or equilibrium vapor pressure is the pressure exerted by a vapor in a thermodynamic equilibrium with its condensed phases liquid at a given temperature in a closed system. The normal boiling point is the temperature at which the vapor pressure equals to the ambient atmospheric pressure, that is, atmospheric pressure of the given surrounding area. Then, lowering of vapor pressure is the difference between vapor pressure above the pure solvent and the vapor pressure of the solvent above the solution. Let P0 equals to vapor pressure of the pure solvent and P equals to vapor pressure of solution. Lowering of vapor pressure equals to P0 minus P. Relative lowering of vapor pressure is the ratio of lowering of vapor pressure to the vapor pressure of the solvent. So relative lowering of vapor pressure equals to P0 minus P divided by P0. Raoult's law of vapor pressure. It states that The relative lowering of vapor pressure is directly proportional to the mole fraction of the solute added. P0 minus P divided by P0 is directly proportional to XS, where XS is the mole fraction of the solute. P0 minus P divided by P0 equals to KXS, but K equals to 1. Then P0 minus P divided by P0 equals to XS equals to N divided by N plus capital N, where small n is the number of moles of solute and capital N is the number of moles of the solvent. Example: the vapor pressure of ether molar mass equals to 74 gram per mole is 442 mm of mercury at 293 Kelvin. If 3 gram of compound A is dissolved in 50 gram of ether at this temperature, the vapor pressure falls to 426 mm of mercury. Calculate the molar mass of A, assuming that the solution of A in ether is very dilute solution. Ether is the solvent and compound A is the solute. N equals to 50 divided by 74 equals to 0.6757. P0 equals to 442 mm of mercury. P equals to 426 mm of mercury. Applying Raoult's law of vapor pressure, P0 minus P divided by P0 equals to N divided by N plus capital letter N. 442 minus 426 divided by 442 equals to N divided by N plus capital letter N. But for a dilute solution, N plus capital letter N is approximately equals to N, since N is very small. Then 80 divided by 221 equals to N divided by 0.6757, N equals to 0.0245, but N equals to mass divided by molar mass, 0.0245 equals to 3 divided by molar mass. Molar mass equals to 122.4 gram per mole. Therefore, the molar mass of A is 122.4 gram per mole. Effects of solute on vapor pressure by Ostwald method. Let A be a solution and B be a solvent. Consider the diagram below. Then the dry air being passed through the two components. The passage of dry air causes the loss of mass. Let W1 be loss in mass of solution, W2 be loss in mass of solvent, P0 be vapor pressure of solvent, P be vapor pressure of solution. Relative lowering of vapor pressure, P0 minus P divided by P0 equals to W2 divided by W1 plus W2. Example: the current of dry air passes through a solution of 2.64 gram of benzoic acid in 30 gram of ether, and then through pure ether. The loss in weight of solution was 0.64 gram and that of ether was 0.345 gram. Calculate the molar mass of benzoic acid solution. Mass of benzoic acid solute equals to 2.64 gram. Mass of ether solvent equals to 30 gram. W1 equals to 0.64 gram, W2 equals to 0.0345 gram, N equals to 30 divided by 74 equals to 0.41 moles. Applying Ostwald and Raoult's law, P0 minus P divided by P0 equals to W2 divided by W1 plus W2 equals to N divided by N plus capital letter N. 0.0345 divided by 0.0345 plus 0.64 equals to N divided by N plus 0.41. N equals to 0.0221, but N equals to mass over molar mass. 0.0221 equals to 2.64 divided by molar mass. Molar mass equals to 125.12 gram per mole. Therefore, the molar mass of benzoic acid is 125.12 gram per mole. B. Boiling point elevation. Boiling point is the temperature at which liquid boils, where the vapor pressure of liquid equals to the atmospheric pressure surrounding the liquid. Effects of solute impurities to the boiling point of the liquid. When solute particles are added to liquid, the solution is formed. The boiling point of solution formed is increased by some degrees Celsius. The boiling point is elevated due to increase in collision of solute molecules and the liquid particles. Finally, the temperature is rise. The difference between the boiling point of solution and the boiling point of the liquid is what we call boiling point elevation. Change in temperature equals to T2 minus T1, where T2 is greater than T1. Raoult's law of boiling point elevation is stated that the change in temperature caused by addition of solute particles is directly proportional to the molality of solution. Change in temperature is directly proportional to molality. Change in temperature equals to K times molality, where K is constant. Change in temperature equals to K times number of solute divided by mass of solvent in kilogram, where K equals to boiling point elevation constant equals to obelioscopic constant equals to Kb. Change in temperature equals to Kb times number of solute divided by mass of solvent in kilogram. Obelioscopic constant Kb is the boiling point elevation produced when 1 mole of solute is dissolved in a kilogram of solvent. Example: when 1 gram of solute was added in 10 gram of water, the boiling point elevation was 1.2 degrees Celsius. Calculate the molar mass of solute if Kb of water is 0.52. Solution: applying Raoult's law of boiling point elevation, change in temperature equals to Kb times mass of solute divided by molar mass of solute times mass of solvent in kilogram. 1.2 equals to 0.52 times 1 divided by molar mass of solute times 0.01. Molar mass of solute equals to 43.33 gram per mole. Therefore, the molar mass of solute is 43.33 gram per mole. Freezing point depression. Freezing point is the temperature at which liquid change into solid state. Effects of solute on the freezing point of liquid. When you add solute to a certain liquid, the freezing point of the liquid is lowered. This is because the solute disturbs the intermolecular forces between the molecules of the liquids. The difference in freezing point of the solvent, pure liquid, and that of solution is what we call freezing point depression. Change in temperature equals to T1 minus T2. Change in temperature is always positive. Raoult's law of freezing point. Change in temperature is directly proportional to molality. Change in temperature equals to Kf times number of moles of solute divided by mass of solvent in kilogram, where Kf equals to freezing point constant equals to cryoscopic constant. Cryoscopic constant is the temperature expressed when 1 mole of solute is dissolved in a kilogram of solvent. D. Osmotic pressure. Osmosis is the tendency of solvent molecule to migrate from a region of low concentration to a region of high concentration of solution through a semi-permeable membrane. Osmotic pressure is that pressure a solution exerts across a semi-permeable membrane to prevent the flow of solvent into it. Vance-Hoff law of osmotic pressure. Vance-Hoff first law of osmotic pressure. Osmotic pressure is directly proportional to 1 over volume. Osmotic pressure equals to K divided by V, where K is constant. Vance-Hoff's second law of osmotic pressure. Osmotic pressure is directly proportional to temperature. Osmotic pressure equals to Kt, where K is constant. By combining the two laws, we obtain osmotic pressure is directly proportional to T divided by V. Osmotic pressure times V equals to Kt. For n moles, osmotic pressure times V equals to nKt, where K equals to R. Then osmotic pressure times V equals to nRT. The above is the Vance-Hoff equation for dilute solution. Isotonic solutions are different solutions having equal osmotic pressure. Hypotonic solution is a solution having higher osmotic pressure than that of other solution. Hypotonic solution is a solution having osmotic pressure lower than of another solution. Colligative properties involving associations and dissociations. Colligative properties are used to determine molar masses of solutes. The value of molecular mass of non-electrolyte, example sugar or urea, obtained from the colligative property are found to be the same as expected from their chemical formula. For electrolytes, the observed molecular masses are found to be either higher or lower than the normal values, that is, abnormal molecular masses. Abnormal molecular masses. The observed abnormal molecular masses is due to number 1, molecular association, number 2, molecular dissociation. Number 1, molecular association. Some solutes undergo molecular association in solutions. This led to the formation of bigger molecular units. 2A associates to form A molecule. Example: acetic acid and benzoic acid molecules forms dimers in benzene while remain normal in aqueous solution. Effects of molecular association on molecular mass of solute. The number of solute molecules decrease. Since colligative properties depend on the number of solute molecules in the solution, hence molecular association lowers the magnitude of any colligative property. Since colligative property is inversely proportional to molecular mass of solute, therefore leads to a molar mass higher than the normal molar mass of solute. Calculation of degree of association. Consider the reaction below. N atoms of A associate to form A molecules. Initially 1, 0. At equilibrium 1 minus alpha, alpha divided by N. Total number of molecules at equilibrium equals to 1 minus alpha plus alpha divided by N. Vance factor I is the ratio of number of solute particles in solution if there is association to the number of solute particles if there is no association. I equals to 1 minus alpha plus alpha divided by N divided by 1 equals to normal molecular mass divided by observed molecular mass. Molecular dissociation. Electrolytes in solution dissociates and give 2 or more ions. Molecular dissociation is the splitting of solute into constituent ions. The number of solute particles in the solution increase. Example: sodium chloride dissociates in aqueous to form sodium ion plus chloride ion. Observed molar mass decrease. The colligative property is higher than expected. Degree of dissociation. A atom dissociates to form N X's. Initially 1, at equilibrium 1 minus alpha and alpha. Vance factor I equals to 1 plus N minus 1 times alpha divided by 1. Vance factor depends upon the state of solute in the solution. When I equals to 1, the solute remains unaffected or unchanged in the solution. When I is greater than 1, the solute undergoes dissociation in solution. Also, I equals to normal molar mass divided by observed molar mass. Modify the equation of colligative properties. I equals to observed colligative property divided by calculated or normal colligative property. For lowering of vapor pressure, P0 minus P divided by P0 equals to I times XS. For elevation of boiling point, change in temperature equals to I times KB times molality. For depression of freezing point, change in temperature equals to I times Kf times M. For osmotic pressure times V equals to INRT. Two components liquid system, immiscible liquids. When two liquids don't mix up to form a uniform homogeneous mixture, the resulting mixture is said to be heterogeneous mixture. The intermolecular force of attraction is greater compared to the intermolecular force of attraction. That is why they don't mix up. AA and BB is greater than AB. Denser components is found at the bottom and less denser at the top, upper layer. Their total vapor pressure is equal to the sum of the pure vapor pressure components. To see the two layers clearly, the immiscible pair is kept in a separating funnel. See the diagram below. When a solute, say Z, that is soluble in both liquids is added, then it will dissolve in both liquids. The ratio of concentration of solute added in a pair of an immiscible liquid is constant. Concentration of solute Z in liquid X divided by concentration of solute Z in liquid Y equals to K. Recall, square bracket represent concentration. Concentration of Z in X divided by concentration of Z in Y equals to K. The distribution of solute in a pair of immiscible liquid is governed by the partition law or distribution law. Partition or distribution law. It is also known as Nernst's distributions law, 1881. It said that when a solute is taken up with two immiscible liquids, in both of which the solute is soluble, the solute distributes itself between the two liquids in such a way that the ratio of its concentration in the two liquid phases is constant at a given temperature. Concentration of X in B divided by concentration of X in A equals to Kd, where Kd equals to distribution coefficient or distribution constant or partition constant. Application of distribution law. Solvent extraction. Liquid-liquid extraction, also known as solvent extraction, and partition is the method of separate compounds based on their relative solubilities in two different immiscible liquids, usually water and organic solvent. It is an extraction of a substance from one liquid into another phase. Example, given solute X, liquid 1 aqueous liquid, liquid 2 organic solvent, ether. Conditions. Liquid 1 and liquid 2 should be immiscible liquids. Solute X must be less soluble in aqueous solvent and more soluble in organic solvent. Solute X be of any amount. Molecular state of X should be the same. That is, no association or dissociation. Temperature should be the same from the partition law. Note, the liquid component which is removing the solute is called extracting component, and that with the solute is removed from it is called extracted component. Kd equals to concentration of X as an extracting component divided by concentration of X as extracted component. Extracting component most of the time are organic solvent like ether, benzene, tetrachloromethane, and trichloromethane. Ether is the most commonly used solvent for extracting organic chemicals from aqueous solution because it can easily be removed after the extraction by simple distillation owing its low boiling point, 37 degrees Celsius. It dissolves most of the organic compounds. Warnings. Ether is highly flammable. Avoid direct flame. Ether vapor has toxic action on human brain. It forms peroxide when exposed to sunlight. Peroxide are explosive when heated. That's why they are stored in brown bottle in a fridge. Example, X is 12 times more soluble in tetrachloromethane than in water. What mass of X will be extracted from 1 decimeter cubic of aqueous solution containing 25 grams by shaking with 100 centimeter cubic of trichloromethane solution? Concentration of X in trichloromethane equals to 2A. Concentration of X in water equals to A. Amount of X extracted equals to m gram. Amount of X remaining equals to 25 minus m gram. Applying partition law. Kd equals to concentration of X in trichloromethane divided by concentration of X in water. 12A divided by A equals to m divided by 100 divided by 25 minus m divided by 1000. M equals to 13.6 gram. Therefore, the mass of X is 13.6 gram. One extraction versus several extractions. Consider the formula below. Y equals to V1 divided by Kd times V2 plus V1 bracket power n times m, where Y be mass remaining after extraction, V1 be volume of extracted solvent, V2 be volume of extracting solvent, Kd be partition coefficient, n be number of extraction, m be initial mass of solute.